What I'd like to do now is talk about how you actually choose the regression line to fit your data. How do you estimate the parameters, the slopes and intercepts in your regression? So we're going to talk about what the most common estimates are and then several different ways to interpret those estimates. First, let's draw a picture. Say we have a predictor x and an outcome y. And suppose x only takes on two values. Maybe x could be equal to 10 or it could be equal to 20. And so when x is equal to 10, perhaps we have a bunch of values of y, a bunch of data points. We have x equal to 10 and y equal to various things. And when x is equal to 20, we have a bunch of data points where x is equal to 20 and y is equal to a bunch of different things. If this is our entire data set, then how should we fit the line? Well, we can take the mean in this group and the mean in this group. We could stop there. There's not much point in actually drawing the line, but we could also connect these dots with a line, and whatever the intercept and slope is here, that's the line. That's the line of best fit. That's the line that best fits those two data sets. What if there's a third group? What if we also have some points where x is equal to 30, and they're the data points? So again, this is the mean of y when x is equal to 10. Here's the mean of y when x is equal to 20. And perhaps here's the mean of y when x is equal to 30. So we could compare a couple different models. We could think about the equal means model, where x is unrelated to y, and the best prediction of y for any point is just based on the overall average. In other words, we believe that these blue dots, the within group means, are just randomly different from the overall mean. We could have a separate means model which says each of these three groups based on x should be considered totally separately. So if you give me a data point with x equals to 20 and you want to predict y, I should consider only the other data points with x equal to 20 and predict just the mean of y's when x is equal to 20. Or I could fit a regression line. I could fit a line that gets as close as possible to all these points, but doesn't exactly go through the means. Because it's impossible to draw a line that exactly goes through these three means, right? But they can't draw a line. They're not on a line. But I can draw a line that gets pretty close. And that's yet another model. So again, if I'm trying to predict the different possible means, the equal means model would say, here's my best guess at the mean of y for any x. The separate means model would say, let's consider each group separately. Here are my three within group means. And the regression model says, let me come up with a straight line, and wherever you are in that line, that's my best guess. If I want to compare any of these three models, the equal means model, the separate means model, the regression line model, I can use the residuals to do that. I can look at how far each point is from each of these possible predicted means. But in order to compare the three models to each other, I also have to know what those models are. I know how to calculate the equal means model, right? I just take the mean of all the y's and all the data points. I know how to calculate the separate means model. I can just calculate the mean of the y's within each of these three groups. But in order to assess whether either of those models is better than or as good as the regression line, I have to figure out what the slope and intercept of this regression line even are. And in order to do that, I'm also going to use the residuals. I'm going to erase this picture now and just redraw part of it just so that it's a little bit cleaner. It's the same picture. Okay. Our regression model is a model for the mean. Looks something like this. The mean of y, if you tell me what x is equal to some intercept plus some slope times x. So what are the residuals then? Well, let's think of this data point. We'll call it y1. This time I'm just going to number the points, 1, 2, 3, 4, etc. I'm not going to number them according to their group and which number they are. Just number the points from 1 to n. Okay. I have data points y1, y2, y3, all the way up to yn for the total sample size. And if I want to look at the residuals, the distance between each of these points and the line, the vertical distance between each of these points and the line, I want to take the actual value of y, and I want to subtract the predicted value of y based on the line. What's that? Well, it's beta 0 plus beta 1 times x1, where x1 is the x value corresponding to y1, to that first data point. I'm also going to put hats on the beta 0 and the beta 1 here, because really, in order to calculate a residual, I would have to already have estimates of beta 0 and beta 1. So beta 0 is our estimate of the intercept, beta 1 is our estimate of the slope. We're going to solve for those, so we're looking toward figuring out what they are. And the residual is y1 minus beta 0 plus beta 1, x1. Okay? What about the second data point? Let me put the 2 here to give us more room. It's going to be the second data point minus the estimated intercept plus the estimated slope times the x value for the second data point. Same thing for the third data point. And the same thing for the nth data point. So if I have n data points and I have a line, I have n residuals. What have we been doing with residuals? How do we summarize residuals? There's lots of ways we could do it. When we started talking about variance, we talked about something called the median absolute deviation. And we could talk about the same kind of concept here. I could take the absolute value of each of these quantities, and maybe I could try to minimize, I don't know, the median of the absolute values of these. I could try to choose beta 0 and beta 1 such that I'd minimize the median of all these absolute values. I could do that. There's nothing wrong with doing that. That's not what a regression is, but there's nothing wrong with doing that. A regression minimizes a different quantity, but it's just a convention. The quantity that the regression minimizes comes from squaring each of these residuals, because remember, if we don't square them or take the absolute value or something, then when we add them up, we'll get 0. So I'm going to square them and then add them up. I'm going to add the sum of the squared residuals for each point. Okay? And I could just stop here. Here's the sum of the squared residuals. If I didn't stop here, I could divide this entire quantity by something to make it look like a variance. Remember, when we calculate a true population variance, we take the sum of the squared differences and divide by how many data points there are. When we were estimating the sample variance in a certain group, we added up the sum of the squared residuals and we divided by n minus 1, because one piece of information had been used up estimating the mean. Here, in a similar way, we divide by n minus 2. The way to think about that is 2 pieces of information have been used up. We've had to estimate the intercept and the slope. This quantity that I've just written here is an estimate of sigma squared. So sigma squared here represents how much the data points vary from the line. And sigma squared hat, our estimate of sigma squared, comes from adding up all the squared residuals and dividing by n minus 2.